Yeah.
Hi, welcome everybody. Hi, I'm Cheryl. I'm Vice Chair at the Toronto SIGGRAPH chapter. Thanks for coming, everybody. Yeah, we're a group of professionals and students that are all interested in computer graphics, and we host events like these. So if you're interested in volunteering or just attending our future events, please talk to me after the event. And I'll have Brock, who's our awesome organizing committee member, give you opening remarks.
Hi guys, I know some of you, so it's great. Thanks everyone for coming. And thanks to folks on the live stream as well. SIGGRAPH's back. Just want to say a few introductory comments. Also, before we start, we've got some coffee and Timbits. Thank you. Feel free to grab some. Thanks again, Cheryl. We're always looking for more help or support, or even just folks, please feel to repost any of our events. And let me just give a quick introduction here to our Jeff Wagner. Jeff will go into a bit of his, I'm sure, as he always is, a bit of his own introduction, but I got to know Jeff, and I've actually realized we sort of met each other maybe 25 years ago or so when we were just chatting there having a quick coffee. So it's interesting. I want to say that Toronto's not very good at talking about ourselves, but we should. Folks like Jeff, folks like Houdini, some of you were at our Alias event, our last event. And something special happened about 25, 30 years ago in 3D software. There was a bit of a downturn, and a bunch of folks said, hey, we need to start companies, and so they started companies, folks like Alias, folks like Side Effects. And this really grew. A lot of people don't realize millions and millions of people that watch movies and are inspired by them for the last several generations are inspired by things that happened with software and 3D graphics that started really 30 years ago here in Toronto. Jeff has been part of that. In fact, he was even before that, and if you don't mind, it's very interesting. I think a lot of folks should know. So if I'm not correct, like in the early 80s, 70s, 80s, Jeff was playing around with computer graphics, wireframing, coding in Lisp.
Lisp.
And the dark ages, if you will. And then he came across things like Side Effects and procedural animation. That really made sense. For those of you that may not know it deeply, for those of you who have heard of it a bit, Jeff will actually show some of these things, all the great things that Houdini, Side Effects and Houdini does as well. And so that Jeff has been involved in the growth from old days to now, really inspiring folks, really getting feedback from customers, people like us, into like what we have now and sort of the next generation of what we're going to see. Mm-hmm. So we're very honored to have Jeff Wagner from Side Effects talk about the newest, latest, greatest, and also maybe some war stories and tips and things to inspire us for the future. Thank you.
Well, thank you very much. So I guess first of all, feedback. If they have questions, you're monitoring as well, right?
Yeah.
Good stuff.
If anybody online has questions.
Yeah, okay, because there might be lots of questions as we go. Yeah, so my name is.
Sorry, Jeff. Did you say it's okay to ask questions as we go, or do you want to?
Yeah, absolutely. Okay. Yeah, I'm very good at segueing and bringing in different ideas and getting inspired by different questions. I've been in the industry indirectly and directly involved since 1993. And I did a contract at Side Effects way back in winter of '93, working with data gloves and characters. So my first foray into computer graphics with prisms back in the day, which was from Side Effects, was actually doing motion capture and doing real-time streaming motion capture to control kinds of different devices, data gloves, flock of birds, the whole bit that was back in the day. And to be honest, motion capture today really hasn't progressed that far. We were doing data smoothing already back then, streaming data directly into the software. So it's come full circle, and because one of the big things inside of Houdini 20 is our push back into character. I see we never left character, but there's been some other advances in other software. And there's some interesting things that have happened with our architecture in the last little while that is going to be exciting to go forward with. Now, Side Effects, the way we've evolved is we've always been this software of last resort. I always say that. if you're working with very different studios and they're trying to do something really complex and they run up against a wall, then they would say, okay, fine, let's try let's try Houdini. And then they throw Houdini at the problem. And if we can't do it, then it's our fault. But we've worked really hard at making sure that this tool set is very adaptable for doing a whole bunch of different tasks within the computer graphics and in the industry. And it just so happens after all these years, we ended up with a software that can do so much that this word platform starts to get kicked around. Can an entire studio sit everything on top of Houdini naked without doing very much coding? And there's a few things that happen to make that an actual reality. One of them obviously is USD, and Houdini adopting USD as a data format. So the very large players, even though they've been working on their own proprietary data formats for the last 25, 30 years and these data formats do have a notion of proceduralism in that as well. They share this common trait of being able to process data as it flows through the pipeline. And that's what Houdini does by nature. So the very first thing we're looking at is Houdini's now this massive piece of software. And the best part about it of all is that all the data plays in the same pool. So that means that every tool that we write inside of R&D, which is right behind us, they make sure that it all talks to all the other data. So, and these operators that we create that work with this data knows how to work with a VDB grid, a volume, versus as if it's a bunch of polygons, or is it Bezier curves, or is it a point cloud. So all of these different data formats sort of pool together into a single geometry pool. So that means that unlike other applications that have to separate this data and have different tools that work with it, the same tools work with the same data. So I can be working with a pool of data in a single operator that has a VDB grid, it has some height field data, it's got like a 20 million point cloud, and it's also got a whole bunch of different polygons in it. And then I can make all the various different data types work with each other. And this talk of using Houdini as a deep data visualizer, a lot of that comes from the fact that we can take pretty much any data and represent it in many different ways, and then give you the tools to analyze that data and do really cool stuff with it. And for the most part, we're just using it to create really pretty pictures. So now we're going to start tunneling into the very specific features inside of Houdini. The first one in Houdini 20 is we've finally refactored all of our old cloud tools. Way back in the day, early days of Blue Sky, we had just introduced our own Houdini volumes inside of Houdini, and we opened up volumes to this language that we call VEX, which is vector expression language, which is used to manipulate any geometry in a shader, and it's a shader language, right, which we refactored to work with data. And I was able to, with their help and direction, within a couple hours, recreate a lot of their cloud tools, proprietary cloud tools that were using simulation that would take a week to turn stuff around. So we was able to sort of do that and save the day, and then they invest a bit in a few cuts of the software, and that's my life. Always being, what I say, that the software last resort, invariably one of us technical consultants would be in there showing the way forward. So long story short, we've now got an entirely new set of cloud tools, refactoring all the old stuff, but all modernized using entirely VDB grids, which are currently living inside of NVIDIA these days, with Ken Museth working on their scientific and research team. And also with VDB grids, they're actually a variant of VDB grids that run on the GPU, called nano VDB grids. And that's what we're looking at here. We're looking at a lot of our VDB cloud tools inside of Houdini. And if you're a Houdini user and you're working with some VDB grids, you could be working an operator that will automatically lift that VDB grid onto the GPU. You wouldn't even know it. So that's the one great thing about working with these tools, is we'll use whatever hardware is available for us to do the work. Yep.
There's some of us that are not as advanced. Could you describe what's going on here?
Yeah, so this is an actual simulation inside of Houdini. We call this Pyro, And there's a network inside of Houdini. It's a graph that can work with data specific for doing simulation. And this in simulation environment can take many different microsolvers and have them talk to each other. So we can create relationships to many different types of solvers. There's another environment out there as well from Weta. They have their Loki tools, which were then going through the Unity workflow. So they have a similar mindset where they can actually have different microsolvers working with each other. And in this case, we have a bunch of microsolvers that are doing all the various different minor components that we can build together to build our own fluid system. There's a brilliant master class done by Jeff Late several years ago where he talks about how to build a fluid solver. And he uses this simulation environment to do that. So definitely do that. But here we've actually moved a lot of these tools from this graph that we use for simulation that, to be frank, a lot of artists have challenges in understanding how to work with simulation data, and we call it DOPS or dynamics. So we've moved a lot of those tools into the geometry context. So it's a lot easier for artists now to work with these cloud tools and also all of the PyroSolver tools that we ported them all to this geometry context about a year ago in Houdini20.5. So in 20, we've utilized a lot of those tools. So with the cloud tools, we have three specific ways of authoring clouds inside of Houdini now. We have running pyro simulations, which we're seeing here. And in this case, we can actually do, or the second way is we can actually model clouds. So we've been modeling clouds for many years. But in this particular case, we got quite enamored with a set of tools that we used for games where they would use spheres to pack shapes and build shapes. And we sort of grafted onto that as a really good idea. So, and Houdini's really good with spheres. So, and we have a whole bunch of tools that can work with spheres directly, in that each sphere has a point, and each point has what we call a p-scale or a particle scale. And we use that to derive the radius of the spheres. And Houdini's all about manipulating these attributes on the geometry. So we're using that wrapped up inside of Houdini digital assets. So I'm just going to pause this here. For instance, some of these nodes are actually what we call digital assets, in that they encapsulate a bunch of Houdini operators into a single operator to make it easy for artists to utilize these tools. And these become more than tools, they become almost like mini applications. And so here we have an operator that basically constructs the cloud shapes dynamically, and then we actually generate those intersection points, which is what we've done. So these are the cloud shapes, this particular operator, and it has an input on it. And many of these operators can work standalone. Oh, I just went backwards. Many of these operators can work standalone in that they don't need an input. Some operators, they absolutely have to have an input. So this one, if you do put an input in here, though, what it'll do is it'll try and fill that space with points. Whether it's a curve, it'll try to put spheres along the curve, or if it's a polygon surface or a polygon manifold shape, it'll try and fill it up with spheres. So that's what this operator does, and it has a whole bunch of parameters on it that allow you to train and change the way that it works. Now later on, we're going to start to introduce the specter of machine learning, which seems to be running rampant across the entire industry. So imagine if I gave an artist the final network of nodes and then gave them a whole bunch of images of clouds, and then they would use every parameter that they had to sort of nail that cloud. We now have a data point for doing machine learning, and we'll talk a lot about how side effects is addressing that later on. But it's really going to be interesting days. Interesting days in the next year, how we do that. So we can see how far we can go with this particular operator. Then we have a second operator. Now this is now TD working in an artist workflow. So a TD, it's Attila, who works at Side Effects. He basically said, you know what, I want to now grab the intersection points, and maybe I can put spheres along that to add even more detail. So now we're at that point where an artist can be a developer working on these tools. And so he adds some more parameters that then randomizes these intersections. And then we have a third tool, which is the ubiquitous VDB from particles. And all this node does is it, given a sphere and a radius, it'll actually give you a little volume puff. So it's basically turning all those spheres into VDB volumes. And it's got some controls for how to generally change the scale of those spheres. And then we have a cloud clip operator. Again, now the artist who built this set of tools built a lot of this tooling for us. And then Cloud Clip actually allows us to add some nice wispiness on the bottom, so we're also, and then Cloud Billowy Noise takes any VDB grid and it adds billowiness to it. And it adds billowy looks to the VDB cloud. So this node really doesn't care about what's happening above it. It's just working on its input. And that's the brilliance of what Houdini is. Each one of these nodes cooks its input and then caches it. And then the next node can access that cache and do work on that. So Cloud Shape from Intersection has no idea what Cloud Shape Generate is doing. It just can see the data coming into it. And I always get well, the Houdini must be very slow. Well, yeah, we've been doing this for over 35 years, so we've got lots of optimizations in there in how we can process this data as efficiently as possible. Because if I make a change up here, all these other nodes get dirtied, and then they evaluate. And that's how Houdini works. There is no let's start modeling in an interface. It has to be a node inside of Houdini. There is no other way around it. Everything starts with a node. And here we have a little node graph. And now Cloud Billowy Noise can create some really nice billowy shapes. And we've added a lot of features to this that allow you to build a really nice looking volume. And that's Houdini. So this really cool cloud tool, you just have to know just about 20 operators, and then you can start working with clouds inside of Houdini. So now we have another one. We have a Cloud Shape Generate with some presets on it, so we can do some different shapes on it. And yeah, I duplicated the slide. Forward. And this is the result. So just from those few operators, we can now create an entire library of clouds that are plausible. And believe it or not, a lot of those parameters can be animated, so you can get some clouds that evolve to a certain extent. And now carrying forward, we can actually take that cloud and add a lot more shaping options to it. By studying clouds and looking at some papers, we realized that a lot of clouds have a wispiness to them. So we created some really cool shaping tools using our Vex expression language to basically create these torn, wispy shapes in the cloud shapes. And we can advect that noise as well. Advection just simply means pulling the volume through space. So we can advect the volume and distort it and add some more features to it. And here we just we can see how much more control we have. And we can also, and as I said before, Houdini can deal with many different types of data. So here we have a convert VDB operator, so we can gleefully convert VDB grids into actual geometry if we wanted to. Or we can change it from a density grid, or a grid that's basically goes from 0 to 1 and just describes density, to what's called a sign distance function. In other words, we can construct a volume that encodes in it the actual position, how far away it is from the surface. And we can encode a value. Basically, that's why it's called a signed distance function, because depending on where the limit surface of our cloud volume is, we can convert that to an SDF, so we know how far away a particular voxel is from that limit surface, and we can encode that. Do all kinds of really cool stuff with these VDBs. Yep.
So the SDF is more or less your distance to the shell of the cloud, right? Because you don't want to lose the transparency, the distinction within.
Yeah, we're taking a lot of liberties. So the reason why this works quite well is the fact that we use spheres to originally build these clouds, right? So you can create some really concave, convex Swiss cheese type volumes that really wouldn't work quite well in an SDF workflow. You'd still could be generating an SDF from a density field, but there could be areas where it's nonsensical data. But yeah.
But the implicit surface will sort of be this conservative shell around.
Correct. Yeah, it uses the density limit surface. Wherever the density is 0, and if the density is goes above 0, then it thinks it's outside. If it's -0, then it thinks it's inside.
Yeah.
So we're just sort of looking at the density shell. Density usually goes from 0 to 1, right? So, and then we consider the 0 to be the limit surface, and then we convert it to an SDF. And we're utilizing the VDB tools, by the way. So there's the open source VDB tool set, which we've tapped into. But that's what we're actually using, that VDB tool set, to do that. So we can calculate an SDF, and from there we can activate a much broader band of that volume shell, and then we can use this as a way of approximating advection of the volume. So from that density, from that distance gradient, we can use that to motivate the cloud in X, Y, and Z directions, so we can actually add some movement to it now. This is the creative side of side effects of Houdini, and it's also this part that I say, learning Houdini is like learning a language, right? You may not know all the words yet, and a word would be an operator. You know, how would you know to put these two operators on the side? The answer is you would have used a file from somebody else to learn and read the scene file, and then ask the question, why did you put that there? And then it becomes a new sentence, and you start to expand your vocabulary. That's why whenever we show a new feature inside of Houdini, the very first thing we get is a chorus of Houdini users asking for the scene files, for the Houdini scene files, because there's no way we can hide any of this. You know, it's unlike any other application where, because everything has to be a node, it's all there. So yeah, it's pretty cool that way. And this is just an example of using the VDB tools to tear this volume apart. Now, you can evolve this a bit more, add a couple more operators, do a lot more refinement on tweaking the parameters, and then once you do that, you can start changing just one of the sliders on that very first operator, just changing the base shape, and then all the other operators just automatically churn through this and give you many different variants of that same operator. So in Houdini, it's very easy to create hundreds or thousands of different variations just by changing a single input coming into that graph. And you don't have to change any of the parameters inside of the graph either to get these sorts of results. So it's really interesting. And this particular workflow is synonymous. I can cover going all the way back to the very early times, you know, Fight Club and the brain that they did in Digital Domain, you know, that intro where they fly through the brain. That same construct existed back then. I mean, they just created a graph to create a really cool brain, and then they could change a single parameter to create an infinite number of different spaces. And then they sat the poor director in front of Houdini at the time, and it just basically, I think it was prisms at the time. It just flew through different variations of the brain until they found a room that he liked, and that's what he worked on. And it just, hear countless stories of being able to use these graph networks to just change the input and generate many different variations. So here's another cloud that looks, yeah, some very evocative, some close-up shots. And we'll get into the shading in a bit later as to how to approximate that. Now, inspired by what customers are doing, we've seen cloud boxes built by customers utilizing Houdini, and invariably they'll want us to sort of take inspiration from that and do it ourselves and do a job that actually plays even better, so that we can take on a lot of the support of those tools. And these fog boxes are a really nice way of building out expansive horizons of clouds. And in this particular case, in this particular operator, the cloud box operator, we even generate the density in such a way that it's plausible that if you increase the density over time, it actually feels like the cloud is actually evolving out of thin air. You know, when the dew point hits the right temperature with the right amount of moisture, you then get clouds forming, and it's quite plausible in that way. And this particular operator has a whole bunch of presets associated with it, so you can use this to do low-level cumulus-type cloud fields right up to the very high, cirrus, wispy, ice-based cloud shapes as well. And you can tile these boxes to create a really large landscape of clouds, which is what we're looking at here. In this case, this is a single cloud box, and it's rendered with our render engine called Karma XPU. And we'll delve a bit into the XPU rendering. In other words, XPU simply means it'll use whatever processor Karma is built against. So it can use an AMD processor, an Intel processor, and actually currently utilizes NVIDIA GPUs as well. So it'll choose what it needs to render the output. Another fly through a different cloud box. This time it's set up to do cumulative nimbus. And again, the important thing to realize is that this is attainable by any artist utilizing Houdini off the floor. And you don't need to know any code or any programming interface whatsoever. You just have to have that mindset of being able to use these Lego blocks to put things together and always expand. Every Houdini artist I know is always expanding their vocabulary and learning all the new operators that we add. And this takes me full circle. So True Lies, right, way back in the day, using curves to generate cloud volumes. And it's about time that we finally got our act together. We can actually do first-class clouds from curves as well. So here we have a simple circle, cloud shapes from line. And now that we got the spheres, guess what? We can then pass it through all of our other cloud tools to evolve some really nice cloud shapes. And this is another example of taking a shape and just basically wiring our squab into that first operator, and then it'll fill that surface with spheres as well. And then it uses all the other operators that we've created to create our cloud volumes. And a couple of releases ago, we added hex tile deforming of volume grids, and that is how we did the animated propeller at the beginning. So we can actually distort and animate clouds by just using what looks like lattice-like tools, where you can actually use a geometry cage with points in between, and you can animate those cages to form your volumes now very easily. So that's quite straightforward to do now. And now switching gears a little bit onto you looking at Solaris and USD. So Solaris is our approach, again, going back to platform. SideFX is always interested in building tools that you can layer on top of. And we were used for Houdini classic workflows using our old object approach to lighting scenes, and we took it about as far as we possibly could go. And then we decided, okay, fine, we want to start building our own scene description language on top of what we've done before. And then we quickly gave up once we saw USD went open source. And so we decided to build our entire tool set directly on top of Pixar's universal scene description. And we're about our 5th year in now, or even their 6th year, if you include prior to shipping. We've built an entire geometry graph-like interface on top of USD. So instead of these operators working with geometry data, they now work with USD primitives. So Houdini 20 is now starting to see a lot more work in that area. But let's start with the render engine. So here we have Karma. We have 2 different versions of our render engine that works directly with USD. And Karma actually uses USD as its geometry scene description. Other render engines, such as Mantra, our own Mantra library our Mantra render engine uses BGO geometry as its geometry format. Other render engines, such as RenderMan, uses its own geometry representation, so it has to convert the scene, whatever it is it BGO, is it USD, it has to convert that into a data format that the render engine can then read and then work with. Whereas Karma, it literally uses the USD library to load the geometry into memory and then refines it on top of that and then renders it. So Karma is implicitly tied with USD for good or bad. So that's what you're getting with Karma. So it's purpose designed to work directly with USD. And Karma evolved around the Solaris workflow as well, so the 2 work very tightly together. And we have 2 different versions of Karma. One's on the CPU, and one's on one we call XPU. CPU, the CPU render engine is explicitly working on the CPU. It's designed to basically take over all the work that Mantra was doing, which is our previous render engine. And it's now pretty much feature complete inside of Houdini 20. And it can do pretty much everything that Mantra could do, and such as texture baking for assets in games pipelines is very important, where Mantra is used a lot, and now Karma is being used to do baking of assets and generate the texture maps that go into the game engine. We've now fully adopted ACES color space inside of Houdini 20, and a lot of render optimizations as it starts to get used in productions as rolled into the latest version of Karma in Houdini 20. And we did a lot of work on render statistics. Now XPU is now finally shipping inside of Houdini. It's production ready. It has full out-of-core capabilities, which is important for texture maps. I can't tell you in a typical studio pipeline when they're working on some effect shots, every asset in itself could have anywhere from 10 to 40 4K to 12K texture maps on that asset. And that can choke a lot of render engines. So a lot of the high-end modern render engines can deal with these textures out of core. So can XPU now, and still take advantage of both the CPU and the GPUs that are available to it. And it has all the features that CPU has now, which is absorption, dispersion, full control over the various different BRDS and BSDFs with albedo. Cryptomats support everywhere. And cryptomats for a render engine has to be able to know what ray is hitting what surface, and then write that to a very specific AOV or an extra image plane that's associated that you can actually use as a mask later on for compositing. So that means the render engine has to be able to support cryptomatch, which XPU can do now. And all kinds of really cool features. So let's get into some example renders of what Karma XPU can do. In this particular render, it's using a lot of lens distortion. We have a long history of supporting whacked lens distortion. We've been used to do all kinds of theme park rides already in the mid-1990s. The T2000 ride from Digital Domain, for example, used a version of Mantra that actually used a lens distortion map. So we have that expectation from our own customers. Yeah, but XPU can be used to render all of the various different procedural data. And one thing about Karma XPU is it just loads in USD. It doesn't even need Houdini. So if you have a USD scene that's created in another application on disk, and it actually is using Material X materials, Karma will be able to use and render that USD file directly. So it's a really good render engine. It's also supported inside of the various different open source USD tools as well. So yeah, it's and we're now noticing a lot more of the renders that are going to the gallery are now being rendered with Karma XPU, simply because it's quite performant and quite comparative to other GPU render engines on the market now. Yep. And in 20 we've go ahead. Pardon me? Oh yeah. So side effects on our website, we actually have a user gallery. And a lot of enthusiasts will submit really cool examples on our website. We have a free version of Houdini called a Houdini Apprentice. It's limited in resolution. I think it's limited to 2K, and you can't write any third-party data format sequences, but you can use it to do any sort of work you want for free for non-profit. Yeah. Yes.
Could you repeat the point that you said about Material X, please?
Oh,
You mentioned something.
yes, for sure. So Karma is not implicitly tied to Solaris or Houdini for that matter. It's a standalone render engine that you can feed it a USD file, and that USD file can have Material X materials inside of it, and it'll render. So yeah, so that means if you're creating USD out of another third-party application, or you just happen to download an entire USD scene, you can actually open up Karma in a shell. Generally, it's done through a shell, and then you can fire up Karma, and then you can literally redirect USD file directly at it using our command line tool called Husk. So you can stream data on the fly into Karma, and it'll just start rendering it. Yeah.
There were some interesting, basically some interesting transport algorithms back in Mantra. Like I believe there was a bidirectional path tracer and things like that. Have those been kind of moved to Karma as well? Does that happen? Or
Not yet. I mean, there's a whole hit list for Karma in a lot of the workflow that it does, and yeah, we'll see. Our mileage may vary, but we still have a lot of things that we need to do. I think Mantra, it's not going anywhere. So if you still, I mean, Mantra is like a Ginsu knife of render engines. It's basically got every render engine in it that's known. I think it even eclipses V-Ray in many ways in what it can do. It has a Ray's render engine. It's got a ray tracer. It was the very first publicly available renderer that I know that could actually marry in-core single memory, ray tracing, and rays, which is render everything that you can see, which was RenderMan. It's just RenderMan, right? And it also has a PBR render engine as well. Yeah, it's a Ginsu knife of render engines. It's not going anywhere. The problem we had with Mantra is that every ray it would hit a surface, we'd have to evaluate the shader. So even though you get an immense amount of power, the problem was performance. So trying to make that really fast and compared to other render engines which weren't doing that, gave it a lot of trouble. Mantra to this day is still being used in productions for doing some really advanced workflow where you really need to have the shader to evaluate every ray hit and to do all kinds of really whacked stuff with the rays. And yeah, it's still a great render engine for that. So as far as Karma is concerned, it's more concerned about performance. And if we need to add any of those extended features, we'll code it ourselves. And then eventually I can see us providing a shader interface of some kind for Karma XPU and Karma CPU, probably in the guise of open shading language perhaps, which MaterialX is based on. So MaterialX uses OSL as its authoring language to create the operators. So yeah, but we do have some nice sweet stuff in Karma CPU as well. So we are now using adaptive. We analyze the scene, use some ML, and we decide where the rays are being propagated in the scene. So trying to solve that deep problem. And of course, we're extraordinarily interested in NeRFs, which are neural radiance fields, and as everybody is, and that's on the machine learning talk. We're going to hopefully have time to address at the very end. But this is basically the graph. So on the lower right-hand side, we have our material builder, and that's where we compose our MaterialX shaders. And some more example of Karma XPU, managing caustics, ray depth level. We can actually determine incidence of refraction between different materials with priorities. Very common in the industry to do this with other render engines, including Mantra, is now fully supported in Karma XPU. And also some more showcasing of the dielectrics. Now, why Karma XPU is so important for us is there's a class of Houdini users, what we call the Houdini generalist. And they invariably end up in advertising or commercials, or they're the very few artists that are used to do the most challenging shots. And to this day, we still have a great sympathy for those users. And there's a great extent of Houdini development that goes to empower these Houdini generalists that can basically do all of these different work together. And so having a render engine that can do all of this is very important for us. And as I said before, Karma XPU is now production ready for use in productions. And it's got a ton of features. Go to our website and have a look at and see all of the different features. Now this one takes me back. So Karma, we actually added an incident rays type shader for rendering rooms. And this takes me right back to my early RenderMan shader days. Way back in the late 1990s, the Advanced RenderMan Guide actually had a section on it on how to actually do this. So you wrote this, and yeah, 25 years later, we finally have this inside of Houdini. We actually have a geometry operator that can take your room with all of its furnishings and then bake out. Remember, Karma CPU can now, and XPU can bake out this data. So we have an operator that can actually bake out all these different layers. But of course, us being side effects and taking inspiration from some cutting-edge game engines, we actually now populate the empty quadrants with slices as well. Again, all supported in this operator. So that means you can actually have procedurally generated rooms inside of Houdini. And Houdini has this really amazing architecture utilizing this graph type called TOPS, or task operators, to automate a lot of the processes for distributing multiple variations on your current machine or on a network of machines. So we just did that. We created 20 different rooms, and then we just ran it forward, and then we filled up entire buildings with it. So this approach does work, as we know. It's being used in a lot of high-end studios, but now it's inside Houdini, and it's available to everybody. And not only that, these texture maps, if you're working with another render engine that also works with that quadrant type texture map, it'll work with that render engine as well. So, as I said before, we work very happily with other tools and other applications and other pipeline setups to basically deliver what is needed to. And it's just some more examples. Now this one's really interesting. Borrowing heavily from games, they have this approach for doing hex tiling of texture maps. So using hexagons to blur the repeatability on tiled repeatable texture maps. And we decided to build a tool as well and ship that with Houdini. And it works in a new Material X operator, or it's a specific operator with Material X. We call it hex tile trilinear material that uses trilinear projection either on UVs or in 3D space. And then you can do really effective hex tiling. And this is where I have to do the Shift F5 thing and then share my screen again. So here we have a really complex model generated. It looks very similar to cloud tools, right? So yeah, you know the scatter, finding where the intersections are and scattering points. It's a common technique inside of Houdini. And then we're just using the hex tile. We're bombing a large an image as an atlas through the hex tile approach using trilinear shading. And this time we're not even generating UVs on the geometry. We're using the position space. And this is a final composed image using the ripple solver, a lot of the procedural tools for generating vines, and using our cloud tool as well as the new skybox to render this entire scene. More than approachable to most artists. Now, on the UX side, development in Solaris we're focused very much on Houdini20 on scene graph. The scene graph details needed a bit of polish, so we went in there and we made it a lot more performant and easier to read for artists. And a lot of tools. We're constantly looking at UX workflows and trying to enhance that. As for the pipeline, we're addressing certain usability issues there. We now have a scene doctor, which allows you to actually figure what the heck is going on with the USD as it's composed. USD has the most amazing composition tools, and you can use these composition tools. And how USD eventually resolves is what we call truth, and every application might have a slightly different version of what that truth is, because these rules can get very complex. So we have a scene doctor in there now to actually see how it actually was composed and how the USD actually evaluated and to build the final constructed scene. Value clips are huge for us because inside of USD wants to cache the entire sequence in memory, regardless of what you throw into it. And of course, Houdini can create like 100 million piece simulation, destruction simulation, and then USD goes, fine, bring it into me, and it wants to cache the whole thing for the entire frame range. USD, that's the way it's engineered. So what you have to do is chop it up into what we call these value clips, which was very cumbersome. And now we've built a whole bunch of tools. 3 or 4 releases later, we now have a whole bunch of tools to make this very artist acceptable. So we even have nodes right inside of USD and Solaris to manage this as well. Look Dev, we're going to take a look at that right now. So we did an awful lot of improvements in Solaris for doing Look Dev. And so we now have a brand new node called the Material Linker. And by the way, I'm going to pause this for a bit because this is the first time, if you've never used Houdini before, this is the actual Solaris USD environment inside of Houdini. On the lower left-hand side is our scene graph tree, where you can see all the USD prims in the current shot or in the current scene. We can take a look at a lot of the values that are associated with these prims. You know, what position, what color, are there any additional data, like what sort of render state it should be in. And in USD, anything can be a prim, from a render product description that tells a renderer how to actually set up prior to loading the USD, to light, camera, and of course geometry, right? And so these materials are USD prims, and they show up in the scene graph. And so we have a new operator called the material linker, and here we have a sublayer that's just loading in a USD scene off of disk, and then we can quickly look dev that material. So brand new operator makes this job a lot easier. We can, on the left hand side, we can add materials, and then we can drag and drop and place these materials as you would expect in any other piece of software for doing look dev. Yeah, we made this really hard in previous releases, but now we're really improved this workflow in Houdini20, where using this specific operator we can now do that. And we have access to catalogs. Not only that, we can load into other third-party catalogs. In this case, we loaded in the AMD Material X library. And not only that, so all the, for instance, the RenderMan materials from ILM, the Lua materials, are supported inside of this as well. So any Material X material, whether it's in USD or if it's a standalone Material X material, can be loaded in and used inside of Solaris and used inside of Karma now. So, and moving forward, you can load in these many libraries. We actually have all the tools that you need to, for instance, doing keyword searches. We can star materials. You can create favorites, categories of materials within these libraries, and all of this data gets saved in the current directory, current artist directory. And if everything's like Houdini, it can be shared site-wide if you want. And now we can load in the geometry tree on the right, and we can create these links for the materials. So why do we need to worry about these material linkers? I've worked on many large feature films that have used Houdini to do a lot of the linking. We always had this thing called bundles, where we can create really smart associations using the namespace. So as long as the pipeline behaves nicely, and for instance, all objects that have glass in them have the name glass somewhere in the shading group, or in the shading name, we can then use wildcards to assign glass liberally to various different pieces in our object. So we can create these really simple rules using simple regex rules. And then comes USD. And USD has its own set of rules for creating, creating these associations. And so that was one of the big issues we had with USD. USD imposed its own language on top of Houdini. And in Houdini20, we're sort of taking that back again and using our own ways of describing wildcards, with a lot of users and artists find a little bit more direct. So in this case, we can implicitly create these rules, or we can use just simple wildcards, just */supports. So that means now we can create material associations with any sort of wildcards. Very important for when you're doing a lot of automated pipeline lighting workflows. And then you can apply these rules. And because this isn't an operator, these rules constantly apply. So if for some reason we change some more prims to actually contain glass, they'll automatically filter through and automatically get the light materials assigned to them. And this is just a few examples of the material library that we're shipping with Houdini now. Now, another thing we're famous for is these fog boxes. Yeah, and this is many times used as a lighting tool. So lighters, sometimes they want to add atmospherics to their scenes. So which is something we could do very easily in the previous workflow. So we now added that inside of the USD workflow. We have a Karma fog box operator. So we can place these fog boxes wherever we want. And Karma CPU and Karma XPU can render these very efficiently. And Karma pretty much gives you real-time updates, and you can get a really good idea of what the density is doing, and it resolves pretty quickly. So this now becomes a lighting tool. So lighters can add more atmospherics to the shot just by simply adding a fog box node in their scene and just changing a couple parameters, positioning it right with respect to the camera, and then hitting render in Karma and getting some atmospheric workflows. And you can see how quick the update is inside of utilizing Karma XPU on a decently configured GPU, of course. And this is just a rendered sequence showing the volume and scattering some particles in there as well. Another example of rendering volumes inside of Karma XPU. This is an ungodly large VDB grid. I think it was generated with millions of points. The same cloud workflow, surfacing into spheres, then turning VDB grids, and then rendering it inside of USD Solaris and Karma. And we also finally, after many, many years, we finally added a proper physical light inside of Houdini, and it's inside of Solaris. So we can now render physically plausible skies using skies and sun. And another thing we did with the hair, fur, and feather workflows is we now can scatter light down the actual shaft of the hair or the medulla. And what that allows us to do now is backlighting of hair and fur is not easy without the medulla scattering. I can tell you, because we haven't had it and a lot of the render engines didn't have this, it really is tricky. Especially the lighter the hair gets, the harder it is to do. But with this, it's actually pleasurable. Finally, you can actually just add a single back area light, and then you get the wonderful light bloom going through the hair and bringing forward to give you the really, really nice, the really nice edge bloom. And white hair, fur, and feathers is really hard to render without the medulla scattering, but with it, it's a pleasure. So generally in production, anything white or light blonde is really tricky, but we've hopefully simplified that to a degree that it actually becomes a lot easier to look at. Now, oceans. Starting all the way back many years ago, there was a third-party Houdini Ocean toolkit, or called HOT, and then we got inspired. We built our first generation of FFT, fast Fourier transform-based wavelets workflow, and so a lot of those workflows work. But now we're in our second generation, rewritten so that it works for all render engines, so through Solaris. And so that's the big breakthrough here is a lot of these procedurals, the procedural Ocean toolkit works through USD now. So as long as you have a render delegate that supports Hydra, you can use that as well. Arnold supports it, RenderMan, Redshift, and quite a few other render engines now have Hydra delegates, which means you can finally render our oceans directly into those render engines without having to go through an intermediate step or writing your own procedurals. So it makes it really accessible now. And here we have the graph. One of the things we did inside of the Solaris environment is many times these procedurals, they get evaluated only when they go through Hydra into the render engine. So in order to facilitate being able to see them in the viewport, we added this new node called the Houdini Preview Procedural Operator. So what this does is it actually builds a lower resolution preview of what this procedural is doing. In this case, we can now see the ocean evaluating directly in their scenes. So really important for lighters if they want to see things in context, or layout artists where they actually want to see the ocean, not just as an optimized flat plane, but actually see the procedural work directly in GL, for instance. So we have an operator that does that. And this will work on all procedurals, including the new feather procedural that we have, hair and fur, and any other procedurals that we have available. And of course, when you fire off the render engine, it'll actually evaluate that procedural and generate the high-resolution data directly in render without having to cache it to disk. So really accessible, really handy.
Question.
Yep.
Any kind of integration points for denoisers out there, like YD and things like that?
Yeah. For sure. So as a matter of fact, Karma CPU and XPU already hooked directly up to the Intel denoiser and the NVIDIA denoisers as well. So both Karmas were engineered to actually work at a low level to be able to utilize any of these open source tools, right, that are available to us. To the point where I'd say that Karma really is leading the whole render engine, how render engines play within the industry. They were both architected on top of a lot of open source tools. And even though we still had to add a lot of our own code to the render engine, slowly but surely, a lot of these algorithms are being made available through open source directly supported on hardware. So Karma XPU, at some point in time, it's just going to be an architecture or framework on top of the actual hardware itself. So what is a render engine at that point in time, right? It becomes utilized by, it becomes more of a general approach to addressing the render problem, as opposed to this piece of software that gets compiled and heavily optimized that runs in its own world, right? So it's eventually going to go that way where rendering is going to hit an equilibrium at some point in time where it's accessible to everybody, not hidden or not accessible through a very specific piece of software like Unreal or Mantra or Karma. Yeah, it's interesting how it's going. And nerfs will have a big part to do with that, I'm pretty sure, these neural light fields. So here we are loading in some USD off of disk. And in this particular case, we're just basically showing you some of the workflows that we've done inside of Houdini. Speaking of rendering, we can now preview any of these procedurals as well. And I'm just going to go a bit further forward here. Just more look at these procedurals, which are becoming very powerful and very potent in that they can now render procedural data at render time without actually having to cache it to disk, which can be an awful lot of data in certain cases. Now, we have this render gallery that we introduced a couple releases ago where we can render to these snapshots, and each snapshot grabs a copy of the USD, the graph, and we write that alongside of the image so you can go in your snapshots. But in Houdini 20, we've actually turned this into a full-on IPR render engine where we can actually see the full stats. We can actually see the render as it evolves within this gallery. So it's no longer really a gallery. It's more like an interactive procedural render interface or an IPR interface. And we've added finally all of these rich statistics that you can get from the render engine available really easy to see. Am I actually even using XPU, which we are, and how many devices do we have too, and how much memory do we have on all these devices? So we finally have a lot of this rich data available to us so we can actually see and tune. Not only that, we write that metadata to the actual image format itself, so if you open up an EXR rendered with this metadata, you can visualize it, all this data through our own mplay viewer. Or not only that, we can actually visualize it as in other viewers as well, or we can even do that inside of HTML. So sort of following the lead that RenderMan, the latest version of RenderMan, they released these really cool HTML interface for visualizing all these different render stats. We have the same thing inside of Karma now. So you can really see what's happening to your renderer, where it failed, and actually get rich logs. Now, inside of now we're going to take a look at another feature that we added inside of it's the Solaris workflow that utilizes the galleries, but now we can take a look at the various different render apps. We're now going to create what we call clones. So what is a clone? A clone allows us to, in this case, it will launch, as soon as we do a local clone, we choose this from the menu. It's going to actually fire off a remote Houdini engine process. And then that process will have hooks into the current Houdini scene. So they'll pass data back and forth. So now what we're doing is we're instructing this remote Houdini service to actually render an image. And we made it so easy to do this. So you can actually fire off 2, 3, 4 renders on our local machine. And as long as you've got a beefy machine, if not, you can set the number of threads to 1, which is what I do, and you can render on my 2080 Ti machine at home. I can render about 4 or 5 of these at one thread before you start to choke the graphics card.
Yes.
So, yep.
So in the fall, what's the use case for doing multiple clones?
It's all about interactivity. So, if, as an artist, as a lighting artist, I might be working on multiple shots. So you can actually see in one, you can change some global lights and see how it affects your various key shots within your sequence. So you might break out 3 key shots within that sequence. And then you can have a clone for each part of the graph. So in this case, these graphs are pointing at a very specific operator in the Solaris graph, in the layout graph, or in the lighting graph, and you can see they're all looking at stage out. But we can change the cameras. So anything in this spreadsheet we can change. So in this case, we've pointed each one of these 3 clones. We call them clones because it's basically cloning the scene, and then it creates a connection and it's running a remote service. The second and more important thing is I can now make any changes I want to the USD graph. And before, if I'm actually tying, if I have a render engine running directly in this viewport, it's actually coupled. It's actually tied in process. So that means if the renderer crashes, it takes out Houdini. So, and in this way, if one of these renders do crash or it just takes all the memory, it won't take down Houdini anymore. So that's the second benefit you get from being able to create these remote services. So there's a lot of benefits to be had
Well,
in this
things
workflow.
look like this, like that, and so then
Exactly.
wait for the whole thing.
Correct.
No, that's not what I want. You can say this.
Oh, you're flying through the lop graph,
And then
making
which one's done?
yeah.
Okay, then you see it while you're waiting for the
exactly. It's this really rapid workflow that you'd expect to have in a 2D compositing application like Fusion. You have many different, or Nuke, you have different render views. It's the same way. So now, and this is we've been told by a few studios that use Solaris exclusively and Karma exclusively that this is the game changer. This is what they've been waiting for. So now they can work with very large graphs, and what would have been a coupled expensive operation. So not only do the expense of generating the USD, you now have you have to wait until it generates the USD into Karma. Remember, because Karma is using the USD and then it refines it, so you're always waiting. Whereas this, you're now just making these immediate changes, and it feels a lot lighter, and you can actually view your updates in these remote renders as well. So, yeah.
Question, these can be distributed on different machines, right?
Yes, they can, yeah.
And how do they share geometry? How do they share scenery? How do they share camera information?
So they're using this technology we call HARS, or Houdini as a service. So we've already worked on a lot of background tools, for instance, that allows you to run Houdini concurrently with Unreal, and the two talk together through this bridge that we've written, and so we're using a similar bridge, Houdini as a service, to basically every time that you create a new clone, it creates a remote Houdini, non-graphical, which we call Houdini engine, running remotely as a separate process, and we're using the same communication. So it's all going to the mothership. So it's this single Houdini scene file with its single graph that's communicating with each one of these remote Houdini engine services. And they can be running on the current machine or through our HQ render farm manager to remote machines. And so it's all, so if we do a change in the glop graph, it'll immediately communicate to the various graphs on to the various graphs that are running remotely on these machines. So,
And if I decide to, for example, change the orientation of one thing, it'll just change the scene description, not the geometry, right?
Correct.
If I change one primitive on something, it might clone that object,
Yeah.
not necessarily any other instances.
absolutely right. Yeah, so each clone could be looking at a different branch of the graph, and that clone would only see those edits that affect its render, so it wouldn't invalidate other render
But it
engines.
wouldn't, for example, if I don't touch any of the geometry in the scene, they're all going to be a shared instance, right? Like,
Correct.
It's not going to
Yep.
waste.
Absolutely, on the same machine, yes, yeah. Pooled memory, yeah,
Or
taking
even
advantage.
on remote machines, would they?
Yes.
I mean, like they would at least pull the same copy from HQ.
Correct, yeah. Yeah. And this is showcasing that a very same setup where we have three sequences within the shot. So it's the typical hourglass workflow that you build up in Houdini networks in general. And now we have it expressed in LOPS, where you have you construct the entire scene, and then you branch out for every shot within the sequence, and you have unique lighting for every shot. And so what we've done is we've created 3 clones, and each one of these clones are looking at the switch. But we can use these context variables to control the shot. And we can add any number of context variable columns within the clone panel, and then we can vary those shots. So in this case we have shot 0, 1, and 2. So what this is doing is each one of these clones now, it loads in its graph, and it has its own copy of the context options, and it's just reading what setting of the context option you've set here in the clone panel. So one remote service is looking at 0, or setting the switch to 0, the second one's setting the switch to 1, and the third one is setting the switch to 2. And you can put as many of these context variables that you want in these different remote clones. But this is pretty much how we're doing shotware. And you can see on the right-hand side each one of the update renders feeding back to the render gallery, which no longer is a render gallery. It truly is the IPR viewer. And we can work. And the only feature I know that we're missing that's key is many of our users are really used to just doing a render region. So just update a certain particular area. We don't support render regions yet within this workflow. And here's a look at using HQ now. Instead of using local clone, you can use the HQ to render to remote machines as well. So now we're getting updates from a remote machine rendering across the network. And that remote machine would have gotten a copy of the graph, and now we can make any changes inside of here. And you can create as many of these as you want on the queue. And the render farm, the HQ render farm, will now distribute those to the various different machines on the farm for you. So yeah, really, really cool workflow. Yep. There you go. Now switching gears. So back to platform. Feathers. This one's a really great story. I remember way back in the day, I was just support. I'd fly into the UK, to London, to support whatever customers needed to. And I always like to say it was the hostile days, and that side effects and Houdini were always used in these by very specific visual effects artists, and always felt like the walls were caving in on us that we had to deliver. And one of the really cool stories was working with CFC back in the day, and they were working on the Phoenix for the very first Harry Potter movie. So we helped, along with Valiant, the movie Valiant at Vanguard, worked on these, what is to this day the core tools for creating feathers. But the problem was you have to have like a bunch of scene files that are handed to in a magic incantation as to how to do these feathers. But over the many years, a lot of our customers had taken Houdini and evolved their own feather tools. So, depending on where you go within and mostly in commercials, believe it or not, commercial facilities would actually have their own homebrew way of doing feathers at different levels of sophistication. But the problem was with feathers is that they're not artist accessible with these third-party tools. So when we're doing feathers, we decided to finally take on feathers a couple years ago. It's a daunting problem. Very technical, but it needs to be artist accessible. So it took a long while for us to work on it and to get the tools finally into Houdini 20. So Kai Stavinsky was the artist that polled, and we interviewed many different customers that have built their own feather tools. And voila, in Houdini 20 we finally have a really powerful set of feather tools that are also used for creating feathers, for grooming feathers, and then simulating feathers. And the tool set is highly performant in that we're lifting and generating the feathers all on the GPU. So, and we just use these regular operators inside of Houdini, and we've built a really nice viewport interface for these feathers. In this case, we have a simple tool that can take the groom, and then we can lay these feathers out, and they're all on the GPU. And the neat thing about these feathers is each one of these is actually a crowd agent. So we utilized our crowd agent architecture, and each one of these feathers is an agent, which means that any part of this feather can be manipulated at any time. And that's what we're showing here. And the nice thing about it is every edit we make to these feathers, every edit that we make to the feather actually gets written to the original point primitive that holds the feather. So on the GPU, as we're moving each individual barb, I just crashed, I think. Oh, it's relaunching again. That was weird. Yeah, but anyway, so each point that represents a feather gets all of this metadata written to the point, and then that point gets put onto the GPU, or it's actually worked on the GPU directly. Oh, it was very kind to me. It actually launched the file again, so that's good. Let's go back to here.
PowerPoint got tickled too much by the feather.
Yeah, I find, and let me go back into here, and I'll actually, it'll figure itself out. So here we are working with the feather tools entirely on the GPU, and So each one of these feathers is basically represented by a point. That's the lowest atomic element to each feather. And what we're looking at here is the GPU that's actually constructing the feather from each point. So it's very much like a game engine, where if we change any one of these points, it's actually just modifying a dictionary attribute on the feather point. And what that means is that that single point then gets distilled however we want, wherever we want. And in this particular case, we're basically working with these feathers. The points get loaded in the GPU. We then construct the feather from the dictionary attribute, from all the attributes from that point. And then we work on the actual resultant geometry on the GPU, which is constantly rewriting back to that point. It's extraordinarily fast. So we can groom hundreds of thousands of curves in seemingly real time on a decent GPU. So these are like cutting edge tools from studio custom tools, now accessible to just as general class operators inside of Houdini. Now, one of the big problems is generating the feathers themselves. So another thing we've done in Houdini 20 is we have a really cool way of distributing weights across surfaces, and in this case we can just add B-spline curves and then define how the shape of the feathers curve, how the barbs form along the feather. In past releases we'd be giving you ramps on parameters and you'd be tweaking around with them, but these days it's much more visual. We're giving you, the artist, the actual B-spline curves to drive the shapes. We also have tweening tools for quickly creating atlases of feathers as well, so we can replicate a whole bunch of feathers and create feather atlases very quickly. And again, this tool allows us to manipulate each feather individually, so we can go in and adjust and tweak the various different controls in the feather. And here's a full feather atlas running through this tool, and we can randomly work on all the feathers individually, or go right inside and use our new paint mask tool. We can actually paint on surfaces now in Houdini, and we can actually paint areas that we want to work on right down to the individual tip of the feather, which was something that a lot of artists had requested from us for many years. So it gives us really good granular control. Yep.
Question. So you mentioned just a bit earlier, correct me if I'm wrong, that when you do sort of modify an individual feather, it does modify the vertex. Does that actually happen?
Yeah, the root point, yes.
Okay.
Yeah.
Well, the thing is that in game engines, especially regarding things that are repetitive, like feather, like grass, you're instancing the same instance, tens of thousands, hundreds of thousands of times.
Yeah.
If you modify the original mesh, if you modify the original vertex, it'll go across. So
yeah.
What I'm seeing now is more like what I would expect for a game engine environment, where you would have
yeah.
like a sort of a modification atlas or something like that.
Correct.
So is this more sort of in terms of like where things are going, or
oh yeah, for sure.
Geometry?
Yeah, I see the work that we did with the feather tools as a new class or approach inside of Houdini. I mean, we now hit this threshold of viewport functionality, of Houdini's functionality, and of a lot of underlying tools. For instance, a lot of this is utilizing the latest version of the OpenCL operator inside of Houdini 20, which is far improved over the one that we had in 19.5. So Kai is actually using this OpenCL operator to write a lot of these tools right inside of Houdini. So not only that's accessible as well.
Right. No, but like your
yeah.
preference is not to modify original geometry, right?
No, every feather is like a crowd agent, right? We're treating it like a crowd agent, so each one is unique. And not only that, we can actually tunnel down into each individual feather. You can have an entire groom of a feather with 150,000 or a million feathers, and you can just grab one barb on one hair and just edit it now, which is something we could never do before in a procedural system, right? So this for us is a breakthrough. It really is in how we can approach procedural systems in a way that artists can work with them. And we got an even bigger one coming in a few minutes in Apex with the character stuff. So yeah, and we also finally, after 20 years of begging, we finally have paint inside of Houdini. We can actually paint on surfaces if there's a UV map. And this was sorely missing in a lot of CFX workflows where you just want to isolate a region but have it also resolution independent. So many times you'd have to dump the vertex attribute out into a paint application and paint it there. We finally have 3D paint inside of Houdini, or 3D mask paint for now. And so we can actually paint these areas. And not only that, we've vastly improved in 20 the way that we can, the way we distribute the weights across the surface. So we're no longer using radial sphere of influence, which is a whole bunch of problems when we're doing simulation and upresing. Whereas now with just a few guides, we can create really complex grooms now. And it's very artist friendly in that if you put a bunch of guides in a specific area, it's no longer overriding that area. It just sort of spreads the weight evenly across, so very artistic, has a very artistic feel to it as well. So we have an entire interface that we built with the radial and pie menus in the viewport that allow the artist to stay completely in the full screen viewport while they work with the tool. And you can see on the upper left we have a roadmap of all the different hotkeys that are available in this particular viewport state. And this state is running entirely on the GPU. And here we are, we can, because we're just mapped the point clouds onto the GPU, we can actually tell the GPU how finely or how coarsely to basically resolve these feathers. So at any point in time we can do quick edits, and we can resolve these feathers in many different levels of detail. As a matter of fact, it could be dynamic per shot, or how far away the bird is from the camera. We can determine the level of density of the feathers or how to actually resolve them. And again, using mask paint, we can paint any of those attributes onto the various different feathers in the viewport. Really cool, powerful workflow. And this is another example of mask paint being used on a character. Just using regular hair and fur rendering, we can isolate a region. And finally, it's resolution independent. So that means if the cage changes resolution, as long as the UV maps are still present, yeah, your mask will be more than relevant moving forward. And again, quickly laying out some fur. So fur and hair pipelines are also now migrated onto the GPU as well. Now, as far as how we can visualize the feathers on the GPU or inside of geometry or inside of Solaris, we can change that on the fly. We can resolve the carves. We can actually turn them into cards. And then from the cards, we can run vellum simulations. And not only that, we can de-intersect them as well. So we actually have a de-intersection operator that can de-intersect the feathers by converting them into surfaces internally and doing that work. Meanwhile, again, it's just writing all that data to the point. And so in this particular video, we're actually just showing some of the basic grooms. So you can actually divide and conquer your groom as well. But we, as I said, we have this new operator that does the de-intersection for us. So we can say the number of intersections and blend. And what's cool about this is the reason why this tool exists is we learned a lesson through our own users in that if you ever get approval on a feather groom that's not de-intersected, it's going to look darker. Yep.
Another question is the intersection tool only available for like the feather system, or can I also use it for all of the vellum stuff?
All the vellum stuff, actually just curves. It doesn't even need vellum, it just takes curves.
Okay, good.
So it can be used to de-intersect curves.
Yeah. Okay.
Is what it does. Curves are surfaces. Yeah. And it doesn't work with simulation. It itself just does that.
Yeah.
So it'll make sure all the feathers are puffed out so that when you do your render to get approvals, you'll finally be able to hit those approvals instead of having de-intersected feathers. The director loves that look because it looks a bit darker, a lot more contrasty. First frame of the vellum sim detangles the feathers and completely changes the look.
Yeah, I was thinking of something, for example, like a ball of leaves that's like,
Yeah, it'll work on that. You have to run quite a few levels of iterations if you think about how to resolve all the intersections and collisions. But yeah, you can definitely use it. It's just a general operator. Yeah. And this is working on the primary feathers with the de-intersection tool as well. So now you can use the Houdini procedural tools to lay out the primary flight feathers and then run it through the de-intersector as well, so that it runs much better through the vellum simulation tools. Yeah. And the whole bunch of text on the grooming tools. But I think the base thing is what we're going to take a look at is the Husk procedural deformer. So that means that in Solaris we can generate these feathers at render time. So we no longer even have to carry them through the data set. So all we're running to the USD file is just the points themselves with the dictionary attributes, and then that gets saved into USD, and then we can evaluate that USD wherever we want. And another thing we did in Houdini was where we're now integrating Vulkan into the viewport, so we're replacing OpenCL and OpenGL eventually with Vulkan, and that gives us an awful lot more control over the viewport. It's currently in beta. It's hidden behind an environment variable, but if you're doing feathers, hair, or fur work, I highly recommend you use the Vulkan viewport because it's just fast. And yeah, and this is just running simulation on the GPU in pretty much real time, or enough to get you a really good idea as to what it's doing. And again, you can tweak everything, and it's much faster in Vulkan than it is on just using regular OpenGL. And as I said, Vulkan is in beta. And there you go. Now this is Karma XPU. Some things surprise you. This one surprised us, is that this was Kai's, when he brought the Eagle in, he started rendering with Karma XPU. He was shocked at how fast it renders. So yeah, and there's a tremendous amount of feathers in here going through Karma XPU. So for some reason, Karma XPU can grunt through huge amounts of curves. It's been optimized in that particular path, and it certainly shows it. And it's got full subsurface scattering on the beak, and using the medulla ray scattering, and then the eyes are being rendered as objects as well. And of course, you get the full performance stats, and you can see the various different look develops, rendering in Solaris. You can get the full procedural at render time, so you don't have to incur the cost until you just render. So you no longer, and you can even simulate on that way as well. Okay, so you can render the simulation, and all the results go into the point cloud as well. Now I'm going to change gears, and because we're going to eventually hit our limit pretty quick, and I do want to have more question and answers, is animation. And again, another story. My first thing I did at Side Effects, as I said way back in the day when I was working, generating some data for SIGGRAPH in 1994 in Orlando, I was showing prisms using flock of birds and a whole bunch of different motion capture devices. So we were actually animation first and foremost. We always were character animation first and foremost. And then my first foray, I remember taking a look at the Hydra, from the Hydra being animated at Disney, and how they were using prisms to animate all the various different Hydra different heads forming, and they had built an entire system on top of prisms to do that. It's just amazing. And then something happened, and then. But we still had this goal of taking our tools and to be at the heart. Kim Davidson, the owner of the company, at his heart, he just loves character animation. So when came time to basically say, let's do this thing in geometry, we went ahead and started working on it. So we have a whole bunch of different ways in which we can make things move. The first one is crowds. So we have these crowd primitive agents that are really compact description of what an agent can do. And we can do all kinds of really sophisticated crowd workflows inside of Houdini. We can do ragdolls, we can automatic lock feet, and we can do a whole bunch of different work with agents. And quite a few studios will use our agents as the core atomic character prim, and then they build their own tools on top of it. But slowly but surely, we're starting to integrate a lot of those tools and offer them directly inside of Houdini. And one of them is ballistic paths. So we now have really easy ways of creating ballistic paths for objects as they interact with characters. And we added sticky collisions finally to characters, since you can have sticky characters with constraints, but the setup is a bit tricky. So we simplified the setup to just a couple clicks now. And now you can have anything stick to agents. You can even have agents stick to agents, so you can have one character roll into other characters before you know it, have a giant roll of characters. But in this case, we're having arrows stick to the character. And then we can trigger ragdoll, partial ragdoll or full ragdoll. This is technology that we've added into Houdini over the years. And so you can create these really organic, rule-based animation systems with agents for doing lots of cool background work. Now the exact opposite. One of the studios that uses us really likes to put agents on paths, simply because crowds more and more are being used for hero characters, right up close to the camera, and using curves to define the path of the agent really allows them to nail exactly where the agent is. Let's say at this particular frame, as we go forward here, you can actually animate the path. But let's say we go to a very specific frame, and we want this agent to move over just a pixel or two and make it a frame earlier. You can actually grab the vertex on that curve and literally go to the previous frame and move that exactly where you want the agent. That's why these paths are so important, because they allow for absolutely precise placement of actors within the shot. So that's what we've done. We sort of inherited that workflow, and we built our own tooling to support that. So now everybody can exactly time characters using these curves, and that's why they're there. So you can actually generate these paths and flow the characters, and you can have hundreds of paths working on the characters. But the real design of this tool is you have like a hero crowd of maybe 5 or 6 or 7 agents now, and you want them to perform directly in the viewport. More and more crowd agents are being used for hero characters, for those agents that are, not the hero agents. Now on to muscles. Muscles are now fully gold inside of Houdini 20. And the way we've architected our muscle tools is to work in 4 distinct steps. And each step works in isolation. And there's particular operators that we built to support each step. The first step would be bones, muscles. Where the bones would be animated, we can drive the muscles based on those bones. Second step would be wrapping that skin around the result of that first simulation, and then we can create fascia and basically blobby steps. And then the third one is where we do the final skin, where we actually compute the fascia, the fat, and then you can get really nice skin. And the fourth step is to add wrinkling. The problem is the actual muscles themselves. If they interpenetrate, then the vellum solver or the FEM solver, mostly vellum these days, will hang up. And so de-intersecting muscles has always been a bit of a problem. So in Houdini 20, we introduced this notion of Franken muscles. So in other words, we give up. So we're not going to spend the 2 to 3 days of trying to de-intersect muscles that were sculpted in another application. We sort of say, fine, we'll merge them all into a single mass of TET mesh, and then we'll build the underlying tissue controls for each muscle. And that's what we've done. So we can basically build ID ranges within this TET mesh, and then we can build the muscle tension lines and treat that region as an individual muscle. And it works very well, but you can see here how we've approached that. So you still want to have sliding interaction between the various different muscles, but in this case we can now have a group for the flank, the rear leg, a different group for the chest that actually reacts to breathing, and we layer on top of that the back and shoulder muscles, and then we layer on the muscles that are driving the front arm. So that means as the character breathes, we can actually have this muscle group slide really nicely. So instead of dealing with hundreds of muscles interacting, you're now only dealing with 5 or 6 key muscle groups, and that's where Franken muscles really come into play. And here we are showcasing some tools for creating the individual muscle IDs. We actually have a customer that took a picture of a pig, and literally took a one of those pictures you see of all the different muscles, how to butcher a pig. He projected that on, and then he just used muscle IDs, and he didn't even do anything other than that. And then that was enough to create the individual muscle groups, and then he did it was in commercials, they had to do it really quick. But here we're actually using a more rigorous approach where we're using the sculpting tools to identify a region of TETs, and that becomes a muscle region. And from that region we can impart all the various different muscle workflows. And all the muscle tools will work with that single mass as individual muscles. Here we are painting the muscle IDs. And then they work directly with the muscle tools. We automatically create the firing of the muscles as they go forward. So there you go. So now what would have been an arduous task of de-intersecting all the various different muscles, we just sort of deal them as massive sets. So it's a really great way to rapidly prototype a character and get it out the door without having to rely on sort of other approaches to doing muscles that try and simplify things. And stepping back a bit, you'll notice that a lot of our muscle tools, and other tools, you actually have to coat the entire character in muscle. In Houdini, the muscle tools are so liberal, we could just have like a ball of a muscle and have just the rest driven by bones. We don't have to encase the entire character. So it's very liberal, and so you can do some really creative things with it. And here's your, again, so this is the muscle pass, as I said before. And then we have that tissue pass, where we're just doing the bag sim, and then we can do the final skin sim on top of that. And this is R&D art, showing just taking a model and just turning it into a muscle, painting some things and just driving some sign motion through it. So as I said before, really accessible for doing all kinds of different things. And of course the Epic video is failing me, so let me go back a bit to that and Shift F5 and then share. So we also did a lot of work with Epic in the MetaHuman project over this Christmas, where they used Houdini to generate an immense number of quasi-static muscle simulations to drive into their ML deformer, which then ended up into the MetaHuman project that they distributed. So all of the training of the muscles was done inside of Houdini. And you can actually download those HIP files from the Epic installer today. And Epic has, they will eventually remove those files, so if you are interested in muscles, definitely install Epic just to get the installer to grab these example files. But you can see the level of detail, and this is all done with Vellum. So using Vellum to motivate the muscles. Very sophisticated work. And now changing gears again, we're going to VFX workflows, making the easy stuff easier. We now have a really nice real-time performing ripple solver that's run on the GPU for doing some really cool things. But whitewater is now added as a first-class citizen in the geometry context, so you no longer have to go into this special simulation environment to work with the whitewater. We've now got geometry operators that can build and construct the whitewater. And these were examples done by Igor Zanik, who is an amazing fluids artist. He uses all bunch of different fluid tools, and we contract him in to basically generate some really cool fluid simulations and test our tools to make sure that they're up to grade. And in this case, he's got flip fluid simulations running with the whitewater simulation, which is pretty cool. Now I'm going to pause this for a bit. So Disney built a set of tools called the FAB fluid tools, or flux animated boundary tools, and they did that for Moana. And what that is they can take any flip simulation and then introduce a smaller container, and by using pressure instead of velocity as the main way of motivating the fluid, animators could then sculpt surfaces and keyframe surfaces. You know, for instance, the water coming up to grab to grab the ship and work with it. So the animators could actually work with the surface clays with manipulators, and then run flip simulations using this FAB workflow. So Houdini 19.5 introduced this FAB workflow, and you can sort of see this traveling container around the elephant that's tracking this elephant. It's really hard to see because we seamlessly integrate that with the previous simulation of the ocean. And we can choose to up-res or down-res. In this case, up-resing a bit so you get a lot more fidelity around the elephant. So all of this now is just click and play. I mean, you don't even have to worry about complex setups. It's pretty much all accessible directly inside of the simulation tool frame. You can sort of see the traveling container around the elephant. And again, you can see the traveling container. So running a high-res simulation, but the whitewater is run across the results of all the low-res and high-res simulations. And here, you cannot see the seams once you do the final simulation, because just the way that we treat all of that. And of course, it's got flying. It's like a smorgasbord of things inside of the simulation test. Now, for the whitewater as well, we also added a new SOP. As we invariably do, we always add new operators, just general operators, and this one just takes spheres and it actually will build the correct intersection and the interference between the spheres, and it builds physically plausible bubbles, including the intermediate space. We just found that doing that added that extra bit of pop in the foam renders. Now this is a ripple solver. We've had this ripple solver inside of our simulation environment. It was slow, it was pokey, and then we ripped it out of there, put it into the geometry context, and put it on the GPU, and now it's super fast. And it supports collision objects. You can provide colliders, and it uses depth to propagate waves, and you can do all kinds of really abstract stuff with it. In this case, we just used the point cloud to manipulate a hex tile. So this is the ripple solver used in a very abstract way, which a lot of our Houdini generalists are apt to do in the motion graphics field. So they're just using the hammer blow to disturb the ripple solver, and then they just project hex tiles on it. And this is artists doing really cool things with the ripple solver on any geometry. So again, showcasing Houdini's object node centric workflow, where every operator doesn't care about what the operators above it's doing. It just works on whatever data passes into it. In this case, it could be a deforming character as well. And we also added a few new operators inside of the simulation context. One of them is wind shadow. We have a wind shadow particle operator, microsolver, and all this does is it just uses a collision object. The problem to solve is that you got your motorcycle rider with a t-shirt, and the t-shirt's rippling really fast, but behind it you just want to have a nice billow. So this is a cheat to get that. In other words, it will basically remove the majority of the forces and velocity in this area where the collider is shadowing based on the wind direction, which, by the way, could be a single direction, or it could be just a random field of velocity. And then you can control, how that, so there could be a cone of incidence where you feather it into this area where there's no pressure, and you just get a nice billow, and you can do all kinds of stuff. So that's what that is all about. Really easy to dial, and it's available both in the vellum context in the geometry, or you can use this microsolver if you're familiar with the simulation environment. And this is just a simple example of using a collider to basically block some wind, which is pretty cool, done by Scott Keating, where he just holds a book and he blocks the wind. And you can also do self-shadowing as well. So the character itself can self-shadow, so that means if the arm passes in front of the character, it can self-shadow. And physically plausible fracturing is our game, so then a customer said, well, do it on spheres, please. So yeah, we added a new option that allows us to fracture glass physically plausible on curved glass as opposed to flat planes as well. Now, visualizers. We're constantly working on making the tools easier to use, these operators easy to use. And by using visualizers, for instance, in rigid bodies, we have these cone twist constraints which are really hard to visualize and work with. And this, I think, is our third attempt at building visualizers, and this time I think we've done a really great job of building visualizers, which are used in Ragdoll. It's used in KineFX for all of our character tools when we're building joint angles for rigid body simulations. And so we also decided, the same developer decided then to build, finally we have our own car rig. It seems to be like an every other 3D piece of software. So we now have built out our own bullet car rig that you can download and grab from the content library on our website. Yep.
Can I take us back to a couple of slides ago?
Sure.
So you had flat panel, or flat pane, you had curved glass, but what
Yep.
about slightly warm Kinder Egg?
Slightly warm Kinder Egg.
Yeah.
So yeah, we could do that. Slightly warm Kinder Egg. So you can use vellum. We have fluids support inside of vellum now. We added that a couple releases ago. So you could use, you could have sort of a fluid, you could use vellum and sort of use that SPH sort of like workflow inside of vellum, yeah.
With like variable viscosity.
Variable viscosity and using constraints inside of vellum to do the break. But if I had to do a massive scale, I would probably move it to flip. Yeah. Yep.
For some of the audience to do explain one Kinder Egg.
A slightly warm Kinder Egg would be a chocolate. Oh, it's a chocolate with a toy inside of it. It's a little capsule. It's got a toy inside of it. And Kinder Eggs are famous for having a very plasticky type of a chocolate to it. So it doesn't really fracture. It sort of tears.
So I made it a little bit difficult, right? So they
Yeah.
can't necessarily do a rigid fracture, and they can't necessarily, just throw it at, just let's say a fluid solver. Like it's in
Yeah.
between, right? You'll have some deformation, some soft body, and then there'll be some fracture.
Yeah.
So this one's-
Yeah. So, and having said that, we're constantly looking at. We originally, before we had flip, we had the smooth particle hydrodynamics, or SPH. And so through our history of solvers, we first thought we could do fluids with SPH, smooth hide, but it proved to be very expensive. But now there's really cool research on how to map that onto a GPU, and so we're always teasing, like inside of R&D, we always tease, do we actually tackle SPH and add as SPH solver back to Houdini? And that would be ideal for doing a plastic, like a sort of like a semi-plastic with some moderate fracturing for a Kinderix.
Yeah, that's the thing. Like in fact, it may not be like actually fluids may not be the ideal thing. I was thinking, like for example, another example would be aluminium foil, like baseball going around. So you have some soft body more than really fluids, and then in there you could have some rigid fractures. So that's the thing. Like kind of throwing some torture cases.
Yeah. So Vellum, I think this is the third release at our attempt at doing a wrap or as rigid as possible structures inside of Vellum. And Houdini20, we actually have a new shape match option. I think it was introduced in 19.5, but really perfected. So now you can do the aluminum foil like effects inside of Vellum and Houdini20 using the match shape option, so you can actually have it be very rigid and then still support all the Vellum fracturing. So Vellum is turning into this multi-solver now. We added fluids as well. You can do balloons. You can do inflation. It supports TET meshes for doing muscle simulations. It can support just raw points, grains. We have this grains option inside of Vellum, so you can actually flow sand with Vellum. And now we can actually add very plastic style workflows by using and introduce rigids with fracturing with the shape match feature, which is using the wrap style workflow as rigid as possible inside of Vellum. Yeah, it's coming along. And also for Pyro, so it doesn't get left out of the rule, more microsolvers are being rewritten in C++ and put onto the GPU. And in this case, we also added gravity-based density. So no longer motivating Pyro by heat, you can actually motivate it by gravity. And we can actually determine what the fall rate is. So, those dust sort of explosions, and not so much the heat convection-based explosions. If you're throwing up a lot of dirt and debris, those options are really great for that. Now this one's a bit of a surprise. So we have these quests during the beta phase. Like every week R&D will package up a file and they give it a quest on the testers. So if you want to be a tester, you're a Houdini user, and you don't have enough time, we're basically removing every excuse possible. But we even give you the files, and all you have to do is run them and give us feedback. So one of the tests was to try the new OpenCL sub. And what we've done here is we've made it almost like our shading language, like Vex. So it now is extraordinarily approachable to all Houdini TDs. So if you know how to write Vex, guess what? We've now made OpenCL accessible to them. One of our artists decided to write a fluid solver inside of the OpenCL operator. So OpenCL can access nano VDB grids for volumes on the GPU. So this is a user playing around with the new OpenCL sub. And Labs is not left out. Labs is always about retiming. So they built a retiming tool, and now they made it so it can retime Pyro sims. This, by the way, is a 1.2 billion voxel VDB grid that we can now retime with the Labs tools. Yeah, and meshing. Last release, we introduced the ability to loading in LiDAR meshes, and meshing in general is everything to do with Houdini in this, what we call this procedural mesh pipeline that is really used a lot in games and a lot in layouts and environments in Houdini, where you build these networks to compose these scenes using procedural workflows. And this whole modeling workflow continues to be added to. One of the tools that is basically in its fourth release now, sees constant improvement, is the retargeting workflow. So Houdini 19.5, we added automatic landmark generation in sort of our retopo tools in efforts to try to make it truly procedural. And for us, truly procedural means pass any mesh in, and the tool without any intervention should give you a really good result. So the automatic landmark generation in 19.5 gave us pretty close to ideal targets that we could then do retargeting of one mesh onto another mesh. And then we were asked, well, now you have to support deforming faces, or deforming meshes. So that's what we've done in Houdini20. So we can actually retarget onto a deforming mesh now. And this is just some examples of that, where we have a target mesh driving a different mesh, and we generate the landmarks, and then we flow those landmarks across the deforming mesh. We also have a quad remesher that's now in beta. So we can take any surface and build a quad topology on top of it. And the reason why it's in beta is because it still has some issues with sharp creases hitting the limit surface and getting that really fine detail. But for organic shapes, it's really good. It's fast. It's extraordinarily fast. That was the one piece of feedback we got from this specific quest from the users, is that a lot of the games, Houdini TDs, gravitated toward this, and they really started putting it through its paces. And they immediately found the issues, which is why it's in beta. But it's just so fast. When we asked them, well, we're going to take it out of the software, there was a cry. They said, don't you dare take it out, because we've already moved a lot of our pipeline to use this. So just even in the beta. So yeah, and it's a great way of generating different LODs from scanned meshes. If you use your iPhone to generate captures, you can then create quads from them, and from there do some work and generate the different resolutions. And this is all it is. So basically, we have our deep scan. We just put the quad remesh, and you can see how quick it is. So. And as I said before, it's in beta because we just can't resolve it yet. But there's a lot of options in there to retuning. We support mirroring as well. One of the requests, which is what we don't support yet, is UVs. So the ability to grab attributes from the original mesh and then have the quad remesher generate those attributes without having to use Houdini's attribute transfer workflows. And again, one of the reasons why it's not there exactly is you can see how all of this detail is being missed by the quad remesher. So still some work to do. And looking at LiDAR scans, 19.5 introduced the ability to load in very common LiDAR scan formats. In Houdini20, we now have a series of operators that can surface those LiDAR scans. So we do all the things such as point reduction, normal calculation, nearest neighbor searches. So we can build plausible surfaces from very dense LiDAR scans, and including the ability to actually manufacture data that is actually not there yet by sort of guessing around the surface and start trying to fill in any areas that were concave that got missed on the LiDAR scan. We try and fill those areas in. And so there you go. Again, platform, right? We're always thinking platform, what tool, and staying in-app. So anytime a user has to go to a different application, we consider that to be a platform failure. So trying to keep everything inside of Houdini, whether or not it's integrating third-party tools via labs or us properly supporting it with our own tools and putting R&D resources behind it. Just some more examples of bringing in LiDAR scans from third-party data. This is from the Thordvassen Museum. And it's just some later scans that we got. We also worked with some customer data, but we can't showcase it here. And this is where my PowerPoint slide says it's almost time to end the day. So I'm going to skip forward, and we're going to go just have a brief look at animation. And so this is the one big workflow that we've been working on, is reinventing animation inside of Houdini. We had hit all the various workflows inside of classic Houdini, and we just couldn't get the performance through. So we completely created kit effects, moving all the animation workflows into geometry, and that wasn't good enough. So the goal here is to make animators work as efficiently as possible in a procedural system. And the one thing we got back from is animators don't want to work with geometry graphs. So what we ended up doing is two things. First of all, building an entirely new graph inside of Houdini, like a new type of graph for describing any sort of procedural operation, but it's compiled at runtime. So it's the exact opposite of when you're working with regular operators in Houdini, where every operator cooks and evaluates. In this other word, you describe the operators, and then you compile it and you run it once. And this particular new graph, which we call Apex for all-purpose execution graph, would take me more than 2 hours to fully explain and get into it. But basically, from a higher level, the problem that we're trying to solve is how can we take a deep procedural system and have an animator actually work with it as easy as they could in another application. Let's cherry pick Maya, for instance. So how can we build applications and workflows inside of Houdini that are accessible as other software tools are? And that's what we've done. So we have this new graph called Apex, where we can actually build the rig. And it resolves itself to a single operator inside of Houdini. And inside of Apex, it can grab all the different geometry operators inside of Houdini, and you can actually build our own data types. For instance, inside of it has support for any number of characters. An animation, for instance, is its own geometry format inside of this new world. So it's a completely open procedural world that could compile at runtime. Not only that, is the graph itself can generate more graphs on the fly. So it's a really cool system. And it hits all the check marks. So an animator can now dive inside of Houdini with a single node, given an entire animation interface. And that's what we're going to look at now, is to see how on point we are inside of Houdini 20. We're not ready yet to release this tool onto the masses, and have it adopted widely. So the first step is make sure that riggers can build rigs and that animators can actually animate in Houdini just with that single operator. So we have the animation interface. We carefully studied the current tools that animators are using. For instance, AnimBot. We have almost all the functionality of AnimBot already built into this new workflow. We have tween machine-like workflows inside of here. But the most important part is that animators work real quickly, and they're given everything they need, and they don't have to worry about anything other than just animating, giving them the function curves they have. Tools and techniques that they're used to, for instance, selection sets, which they're used to in working with other software. So in other words, the selection sets do the picking for you, and the Apex graph actually determines what attributes get promoted to the animator, like do they get translates, rotates, or scales, or all three. So very familiar workflows that you would see in other 3D applications now presented to the rigger, and the animators just work on animation. And we actually have a really good in-house animator, Warren Leatham, who I've known for over 25 years. Can animate in Houdini in the early days, but also is a very good Maya animator as well. So he's a great resource to have to work inside of R&D to help the developers build these tools. And the other thing in this environment is, and everything becomes a prop, is a rig. So in this particular case, we've introduced a chair, and we just put a single locator at the base of the chair. Now the animator grabs this, and then they can rig however they want in this state. So in this case, they're creating new locators. In other words, they're rigging, and they don't even know it. They're just adding locators to the rig, and they just put it in a simple parenting hierarchy using that state, and then they can animate the chair along with the character. So as long as you throw the chair into the mess with all the other characters and just put a single locator on it, the animators can do the rigging on the fly in keyframe. And again, they haven't created a single saw. They haven't created a single node. They're working on top of that single operator. So, and they're just generating the data on the fly by running little Apex routines. And another thing with this environment is you can go so far without even using any constraints. And not only that, we can finally play QuickTime movies on hardware. Yeah, so previous to Houdini 20, we couldn't run QuickTimes in hardware. We had to run it through software, so they were dog slow. So we worked our way around. For some reason, all of these restrictions with utilizing graphics on hardware is still in place. So we finally have a way to visualize QuickTimes really quickly in the viewport like every other major software can. So animators can now visualize videos alongside their characters as they animate. Simple, trivial tool. Now this is interesting. There's not a single physical constraint between these characters. So we have an environment now where an animator utilizing an interface and hotkeys can now quickly animate many characters at the same time. And the reason why we're able to do this is because all the characters, first of all, live inside of this single environment. And secondly, the viewport state can crack all the transforms and all the apex graphs that are being evaluated on the fly. And it's all done really quickly. And you can see here we have a tween machine-like interface where we can do in-betweens keys, we can blend to neighbor, blend to frame, ease, blend to ease. So we have all of these controls that animators are very used to already in place in this environment. Now, animating props that characters interact with in this new state without utilizing constraints is pretty quick. And even though this looks like it's a dense, it's an animation interface that looks like it would generate a lot of dense data, we're always trying to write all of the different constraint data back to the original keys. So we actually can add physical constraints if we want to, though, and in this case the animator is actually adding physical constraints between these hands. So that means in between there's an actual constraint between the prop and the hands. Now in Houdini before, the animator would have to deal with a whole bunch of different steps, and now it's just really straightforward. We just generate more graph. We just generate a graph to describe this, and the graph gets saved to disk. The animator can share this graph with other animators, and they can get these constraints on the fly as well. And not only that, we can always write the results of the constraints back to the original keyframes as well, in case you want to toss the constraint away. At the end of the day, we have to bake into USD anyway, right? Cool. And then here is another example of utilizing just doing some basic blocking. Animator's just done some basic blocking, and then you can grab the COG and you can generate a motion path from that. And this is a part of the tools that the animator has inside of these Apex rigs. So they can generate these ballistic paths. And animators would probably hate this because they're used to keyframing everything. But what I tell the animators is, back when I learned how to do animation drawing, you use the tables from the Illusion of Life, the Disney animation tables. I just call this a cheat sheet just to get the animation tables and they're running ballistic paths. But the key here is we can actually manipulate this COG. But the most important part is, at any point in time, we can write the results of that animation layer. We can bake it back to the original keys if we want to, and it's all done procedurally. So and then we can take the paths, bake it back to the original keyframes, so the animators are happy. They don't have to deal with dense data at the end of the day. They just use the paths to drive into the final animation. And so that's the end result. You can actually, running the final result with the paths and the animation blocking it all out. And so the whole idea is about animators delivering more animation per week. I'm going to bypass these. So again, we can trigger, the animator can actually keyframe into ragdoll as well really easily. So in this particular case, the animator is setting up the motion, and then they can add, in this state, they can add ragdoll at any point in time. And then the characters get turned into their representative rigid body representations, and then they can trigger ragdoll, keyframe into ragdoll at the end of the day as well. So there's a couple other animation systems that are now approaching ragdoll as well and utilizing it in this specific way. So then the animator can then work with that and add ragdoll in a really controlled way. And again, at the end of the day, they can bake the results of the ragdoll into the actual keyframe animation of the characters blocking, and you can see there's dense data here in the keyframe in the lower right hand side where he's just said, screw it, I'm just going to have the dense data keyframe per frame. So I don't really want to work on that. But we also have tools that can do keyframe reduction as well. So we have a lot of those functionalities there as well, so you can reduce the number of keys in there as well. And the animator can freely integrate ragdoll into the entire animation interface in the animation workflow. And there's just triggering ragdoll on the keyframes. So making it all active. And that's pretty much the end of my presentation. We can start diving into Apex. We had another hour, but there's going to be lots of master classes coming in the future as to how we're doing this whole rigging interface. Other than we have quite a few example files available to us on our website. We have the content library. So that's my presentation so far. And now I'll open it up for questions. If there's anybody got some,
I
yes.
have a question first. Curious how many folks here use or have used Houdini? Great.
Yeah, very
About,
good.
a quarter of the folks here.
Yep, very good. You can do. Yep, it's great to know. Yeah.
Any questions? Feel free.
Yes.
Yeah, now that we actually talked about animation, I'm not an animator, but I remember there was one function in actually After Effects, which is not a 3D software, which I loved, which was it recorded your mouse click. So, for example, if I would want to animate a sphere, I could, like, in the viewport, just, like, very nicely move my mouse and the sphere like I want to animate it, and it was recorded. And I was wondering if this is something that's also, like, possible.
Yeah, for sure. We've had there's a component of Houdini that is not used very often, and we call it chops or channel operators. Yeah. And that's one of the first nodes we put in there already in like 1999, 1998 was the mouse chop. So you can already do that in Houdini right now. Yeah, so you can put down a mouse chop, and it will actually give you the coordinates of your mouse and your viewport. And you use the print screen. Use the print screen button to make it live and not live. So at any point in time, when you've got this, you could be anywhere in your interface, and you hit print screen, and it starts recording your data.
That's awesome to know. Thank you so much.
Yeah, and the keyboard. We have a keyboard chop as well, so you can actually record keyboard strokes as well. And yeah, all of that stuff is all old stuff. Now we have modern equivalents inside of KineFX. And I can imagine that all of that is eventually going to end up in Apex. So we'll be able to do all of that. We already have a keyboard, a gamepad support inside of Houdini in general, including in this chops interface as well. You can have all kinds of different interface devices. But slowly but surely, we're taking a lot of that chops workflow and migrating it into a more modern threaded environment. So Apex is ripe to basically get a chops port. In one of these years, we'll see. We'll see if we get enough developers to do that. Yeah. But yeah, you can already do that today. Yeah.
I have a few questions.
Yep.
So two. The first one is, you've seen this for like 25 years. What are a couple of things that really stood out in this version? You're like, wow.
Oh, something we didn't cover, which is machine learning. So there's we should have a separate meeting and just all the minds about machine learning and what direction it's going and what impacts it has on the industry. I have a fairly good track record at because I'm front line. I work with all the customers, and I take the software and project it to them and give them all kinds of ideas, and they throw all kinds of ideas back. I can safely say that even small studios and large studios will be utilizing their own machine learning by at least late next year. So not only are they relying on open source tools with questionable scraping of data sources, where the real gold is every artist themselves training their own machines and utilizing that to drive own variations of their own artwork. We've already have two examples of that already available in the content library. One where we're using our animated capybara, where we run it through 150,000 calisthenic steps, poses, and we use ground truth to train a machine, which, by the way, it takes like 17, 18 hours to generate 150,000 poses, and only takes about a minute and a half to train the machine. And we also saw early instances of that at Sony into the Spider-Verse, where they used Houdini and the facial motion. So the animators were animating the faces, and at the same time they were training their own machine. So if you're going to get an animator to use ML, what better than to actually have their own animation be used to train the machines that they're using? So that's the direction that SideFX is going. We don't want to get into the whole world of scraping data. And there's a danger to that as well if we were to invest a tremendous amount of effort and money to scrape data, build our own machine. We're now competing against other companies that are doing the same thing. We'd rather have nodes with parameter interfaces and then train the machine against the current state of those parameter interfaces. So you could we actually did that with the train tools, which we didn't look at. But the train tools, we actually we can have a quick look at that, because that's.
So you say terrain, not terrain?
Yeah, terrain. So I'll show you a bit of that. So we'll show a bit of a graph. So we actually have on the content library now the ability to actually paint features. And we brought in an artist to actually build all this data, which we then used to train the machine, which we're actually utilizing now to to actually paint this data. And not only that, Houdini ships with Onyx, ONNX. And Onyx is it's an open source set of tools that enable an application to both train and utilize inference models. So that means right now in Houdini 20, if I train a machine and I build the logic and I just create an operator and I just distribute the operator to anybody using Houdini 20 right now, you do not have to download anything to actually run that machine inference inside of Houdini. So we're sort of leading the way in that particular realm right now. And objectifying machine learning is just, and it's your data that we're training against, not the other people's data. That's the goal, right?
Quick comment on that. I was here, full disclosure, last week for Michelle's talk on that machine learning stuff.
Yes.
So the thing is, the number of weights was 900 times 128.
Yeah.
That is fairly large.
Correct.
And the thing is that you'd have to spend all that time training on the capybara only be able to reuse it just on the capybara.
Correct.
It feels a little overfitted. Is there any sort of plan to say, have a more general, smaller model that's just, deformation, it's just, for muscle, for whatever, and say, try and reuse that, throw it at different rigs, different.
So it's my first word is it's early days.
Okay.
It is very early days, and we wanted to start from an area that we knew would give us success in a short period of time. So utilizing the work that was pioneered at DreamWorks, where they used it's a delta model where you look at your target shape, you look at your joint angle, and you derive a relationship from that. Yes, you get a tremendous amount of data points from that. But the terrain setup is a little bit more direct, right? In that it's a little bit more in the different type of machine learning. It's more image-based, and as soon as you go towards an image-based approach, let's face it, in a way, if you understand what's happened, in a way, you would think that we'd be far more along than where we are at right now. I think the one thing that's made this possible is obviously hardware, right? GPU hardware, basically making this more accessible, and being able to train these machines in a very quick period of time. But yeah, it's still early days.
The image-based suggestion, I would actually, because you showed the hexagonal tiling thing for getting better repetition, there's some really great papers on using ML for multi-layered decals that are repeatable and things like that. So
yeah, did we mention that we're working on our own in-house compositor? Which we are, and it's going to probably end up in Apex as well. So Apex will be able to do massive image processing as well, and Apex supports multiple inputs, multiple outputs. So that means, yeah, it's just, yeah. So we are working on that to fit inside of that world. Yeah, for sure. So that's coming. But yeah, so, and then the capybara, you're absolutely right. But remember, in production, you really want to have that narrow model. You know, if you're using a specific actor, and that actor, if it even strays 1 iota from what that actor looks like, they won't accept it. So having these really targeted, you know, solutions is very important for the field that we're in motion graphics. So the training time is minimal. Generating the data to train is excessive. But then again, you have to know Houdini. Houdini is brilliant at building these sorts of procedural systems that can build the correct data to train against. Right? It's really good at that. I mean, we have a lot of uptake with a lot of the machine learning. You know, the different organizations that are using to create synthetic data, for instance, for doing autonomous vehicles, anything autonomous, whether it's robots working on manufacturing. Invariably, they'll have Houdini in there generating the synthetic data, simply because they can control it. And my belief system on this is, you can listen to anybody if you want. My artistic view of machine learning and bias is that bias is inevitable in training. There is no way to remove bias out of this. No way. And that's why, by embracing bias to the point where it's a single individual that is biasing that machine, and there you go. But to get more general models, you're now starting to, you know, to simplify the model, you're now starting to have to deal with a much broader set of data, right? And try and find a way forward to actually make that work. Yeah.
So,
Yeah, it's a different thing altogether.
but
But that's the one. That's the one thing. Yeah.
Yeah. No. Thank you so much, Jeff. Thank you so much.
Yep.
We're going. I know some folks have to leave,
You
so
bet.
we'll just finish. Thank you so much. We'll
Thank
finish
you
up
very much.
here. We are going across the street, folks, to Jack Astor's. If anyone wants to join, of
cool.
course yourself, and if anyone wants to, stay behind for a few questions, if that's okay. I don't know your
Absolutely.
schedule, but we'd all appreciate it.
Yep.
Jeff,
I have the evening.
Cheryl, and I really, and the rest of the folks here at